Welcome back to the next video, everybody. Today, we're going to be looking at Galois representations attached to weight 2 Newforms. So let's get into it. We're going to have to journey a little bit into the realm of modular forms here. We're going to have to give a crash course on modular forms first, or none of this will make sense. So let's take a natural number n. We'll define gamma of n to be the set of matrices in SL2Z. SL2Z is the set of 2 by 2 matrices with determinant 1 with integer coefficients. And gamma n is the subgroup there of matrices which are equivalent to the identity matrix when you reduce all the entries mod n. Now, gamma n is a subgroup of what we call gamma 0 n, which is the group of matrices A, B, C, D, and SL2Z that reduce to star, star, 0, star mod n, where star is anything you like. Although, look, these stars don't all have to be the same thing, okay? And it's gamma n is also a subgroup of what we call gamma 1 of n, which is a normal subgroup of gamma 0 of n. And that's defined to be all matrices A, B, C, D, and SL2Z that reduce to 1 star 0, 1 mod n. Okay, so gamma n is in gamma 1 of n, is in gamma 0 n, is in SL2Z, right? And these three groups, gamma n, gamma 0 n, gamma 1 of n, they comprise the most important what we call congruent subgroups of SL2Z of level n. In general, a congruent subgroup of SL2Z of level n is just a subgroup of SL2Z that contains gamma of n. Okay. All right. Let's let H be the complex upper half plane. We'll let GL2 plus of R be the group of 2 by 2 matrices with real entries and positive determinant. There is an action of this group on H by what we call fractional linear transformation. Here's the action. For gamma equals ABCD in GL2 plus of R and Z in the upper half plane H, the action will be defined as follows. Gamma acting on Z, or gamma Z, will just be AZ plus B over CZ plus D. Okay, it's an exercise to check that this actually lands in H, but you can do that. All right, here's another action we want to know about, the bar action. Let's let K be a natural number. If F is a holomorphic function on H and gamma with entries A, B, C, D is in GL2 plus of R, we can define F bar K gamma of Z to be the determinant of gamma over CZ plus D to the K times F of gamma Z, where gamma of Z was defined on the previous slide. This is, well, this is easy to see, but this is a right action of GL2 plus of R on the space of holomorphic functions on H, and I'll call it the bar action. Okay, so what's a modular form? Let's let gamma and SL2Z be a subgroup of finite index. A modular form of weight K for gamma is a holomorphic function F on H satisfying two properties. It's invariant under the bar action under gamma for all gamma and big gamma. So F bar K of gamma is just F for all gamma and big gamma. And then for every delta in SL2Z, so not just the deltas in gamma, but all deltas in SL2Z, there is a Fourier expansion of the form F bar K delta of Z equals the sum over integers n at least 0 with Fourier coefficients a sub n times q to the n over m for some m and n. Now, for our purposes, m will always be 1. Okay, so you can just think of this as q to the n here. And what is q? It's e to the 2 pi I z for z and h. Okay, look, there's really just a couple of things you need to extract out of this second condition here. First of all, another way of saying this, and there's good reason for this that I won't get into in this video. The second condition is often just stated as F bar K delta is holomorphic at the cusps of gamma. So you can remember like F is invariant under the bar action and F bar K delta is holomorphic at the cusps of gamma, or some people might even just say F is holomorphic at the cusps of gamma. But the second thing is this: if I give you a modular form of weight K for gamma, what happens if you plug delta equals the identity in here? You just get F of Z here. And so that you get F itself has a Fourier expansion sum over n at least 0 a sub n q to the n. Okay, and that's how we're going to be writing down our modular forms from here on out with Fourier expansions. Okay, how about cusp forms? If in addition to all of those conditions above, for every delta in SL2Z, A0 is 0. So this first coefficient here vanishes. Okay. Another way of saying that is F bar K delta not only is holomorphic at the cusps of gamma, but F bar delta K vanishes at the cusps of gamma for each delta in SL2Z. So if A0 is 0 for all delta, in other words, F is what we call a cusp form of weight K for gamma. Okay. Now, if gamma is a level n congruent subgroup of SL2Z, then we're going to say F has level n. Okay, so a modular form and or a cusp form will have a weight K and a level n typically, because for us, gamma will just generically be a level n congruent subgroup. Okay, here's an kind of a key example of a cusp form. The Dedekind eta function is given by eta of z equals q to the 1 over 24 times the product from n equals 1 to infinity of 1 minus q to the n, where q is e to the 2 pi iz and z is in the upper half plane h. And then the modular discriminant is delta of z, which is defined to be 2 pi to the 12th times eta of z to the 24th. Now, this turns out to be a weight 12 cusp form for SL2z, so for the full group SL2z. In fact, 12 is the smallest weight for which there is a cusp form for all of SL2z. And what is this? Why is it called the modular discriminant? It's none other than the discriminant of the standard complex elliptic curve associated to a given torus C mod the lattice generated by 1 and z via the uniformization theorem discussed several videos ago. So discriminants of complex elliptic curves are somehow modular forms, cusp forms, actually. Okay. Okay, so notation, the complex vector space of modular forms of weight k for a given gamma is denoted mk gamma, and the subspace of cusp forms is denoted sk gamma. You can show that these spaces are always finite dimensional. This is done in Diamond and Sherman, for example. When gamma is gamma 1 of n, we have kind of shorthand for mk gamma and sk gamma. We don't write mk of gamma 1n, and sk gamma 1 of n, we just write mkn and skn respectively. Now, if I give you a Dirichlet character chi mod n, so a character, a multiplicative homomorphism on z mod n z cross to c star, we denote by mkn chi and skn chi the subspaces of mkn and skn respectively, consisting of those f such that f bar k gamma is chi of d times f for all gamma with lower right entry d in gamma 0 of n. So look, you're taking things in mkn such that they are not invariant necessarily under the bar operator for all gamma and gamma 0 of n, but they kind of almost are. They're invariant up to a twist of the character chi by entries in d, where d is the lower right entry of little gamma and gamma 0 of n. Okay, so these are very important subspaces. Why? Well, we have these eigenspace decompositions. Basic representation theory actually gives you that mkn breaks down into a direct sum over Dirichlet characters chi mod n of the mk and chi's. And similarly for skn. Skn breaks down into the skn chi's, where chi runs over all Dirichlet characters mod n. It's worth noting that if chi is the trivial character, which it very frequently will be for us, what is mkn chi and skn chi? It's actually just mk gamma 0 n, the weight k modular forms for gamma 0 n, and sk gamma 0 of n, respectively. Okay. So we're going to need kind of a very brief, disturbingly brief crash course in Hekka and Diamond operators here. Let's let n be a natural number, let's let p be prime, and let's let delta sub p denote the set of 2x2 matrices with integer coefficients and determinant p, which when reduced mod n give a matrix of the form 1 star 0 p. If I give you a weight k, we'll define the pth Hekka operator on skn as the following linear operator tp from skn to itself. What is tpf? It's p to the k over 2 minus 1 times the sum over delta of f bar k delta, where delta runs over a complete set of representatives for the distinct right cosets of gamma sub 1 of n in delta p. Okay, so you can actually say what these right cosets are. I'm not going to do that here. I have a whole video on Hekka operators. Well, I have several videos on Hekka operators in chapter 3 of my notes. Those videos are already up actually on my channel. Okay, these operators are well defined. They're independent of choice of representatives. They preserve the character eigenspaces from those decompositions above, those direct sum decompositions. So we're all good. How about the diamond operators? Let n be a natural number for d and z mod n z cross. Defined the dth diamond operator bracket d as a linear operator on S2n, given by the following. What is diamond d of f? It's f bar k gamma, where gamma is any matrix in gamma 0 n with lower right entry big D, where big D is equivalent to little d mod n. This is actually well defined, believe it or not. And it also preserves character eigenspaces. Some people also call these Hekka operators in addition to the Hekka operators TP that I gave you above. Okay, laughably bad but accurate definition of Newform incoming. So loosely speaking, a weight k Newform for a congruent subgroup gamma of level n is a weight k cusp form. So it's like a special kind of weight k cusp form for gamma, which doesn't really come from a weight k cusp form of any lower level than n. Okay, this will be made precise in chapter 3. That video is already up on my channel. But look, this isn't really what we're going to think of as a new form. It's not just a cusp form that doesn't come from a lower level. What that is that is an element of the space of Newforms if you want to call a cusp form and actually a new form and not just an element of the space of new forms, you have to require more of it, which we're going to do right now. So we are going to be very interested in weight to normalized new forms of conductor or level n and character epsilon. So what are those? So take a new form f in S2n with the Fourier expansion sum from n equals 1 to infinity a sub n q to the n as usual. Okay, that already takes care of the weight to level n business. What does normalized mean? It means the first coefficient a1 is 1. So we've taken care of weight to normalized. We kind of know what new form means. We know what level n means. Okay, what does character epsilon mean? Again, you already know this, but let's recall. Such that for some Dirichlet character epsilon from z mod n z cross to c star of conductor n, the conductor being the lowest possible level of epsilon, we have f of gamma tau is epsilon d times cz plus d squared f of tau for all gamma equals abcd in gamma 0 of n, and for all tau and h. Okay, so that takes care of the character epsilon. So we've defined this, kind of this, and this. What does it mean that f has conductor n? It means n is the minimal positive integer satisfying the above properties. It's like the lowest possible level. Now, since f is already a new form, you can use the words conductor and level sort of interchangeably, because new form already means you're not coming from a lower level, although it means it in a more strict and precise sense that I'm willing to get into here. So I still have to fully tell you what I mean by new form, though. I don't just mean doesn't come from a lower level. I mean more than that. I'm also going to demand, if something wants to be called a new form, that it be a simultaneous what we call eigenform for all of the Hekka operators TP for all primes P, and for all of the diamond operators diamond of D. What does that mean? What does it mean to be in simultaneous eigenform for these operators? It means what you think it means. It means there exist complex numbers lambda sub P such that TPF is lambda PF for all primes P. In other words, F is an eigenform, and the lambda sub P's are the eigenvalues. And then a similar statement should hold for the diamond operators diamond D for all D and Z mod and Z cross. There should be eigenvalues there as well. Okay, so when I say weight to normalize new form of conductor n and character epsilon, I mean all of this. And I even wasn't fully precise here because I still haven't exactly told you what a new form is, but I've given you enough to go on for now. Okay, some basic properties of new forms you just want to keep in mind. The space of new forms under the less restricted definition, S2 of big N with this like superscript little n for new, has a basis of new forms under this new, more restrictive definition of new forms. So that's one theorem. Okay, this is covered in Diamond and Sherman. I think the DDT notes also talk about it. Moreover, this is very important. The TP eigenvalues lambda p of such a new form F with Fourier coefficients a sub n under the newest strictest definition of new form are exactly its Fourier coefficients a sub p. So a sub p actually is the TP eigenvalue of F. That's nice. Another really nice thing is if n and m are coprime, the n-mth coefficient of F is actually the nth coefficient times the mth coefficient. So the coefficients are multiplicative. All right. So last little bit of setup before we get to the big theorem of the day. Let's let P be a prime. Let's let F be a weight to new form of level n and character epsilon with coefficients a sub n. Let's let K sub F be the finite extension of QP generated by the Fourier coefficients of F. I mean, you have to prove that's a finite extension because there's infinitely many coefficients here, but it turns out that that is a finite extension that's called the local, so K sub F viewed as Q adjoin all the Fourier coefficients is called the number field of F. So K sub F is kind of the local version of that at P. So big theorem of the day. Theorem, Galois representations attached to weight to new forms. There exists a unique, odd, absolutely irreducible p-adic Galois representation rho sub F from GQ to GL2 of K sub F. In fact, we can even choose coordinates such that the image lands in GL2 of O of F, where O of F is the ring of integers of K of F, which is unramified at all primes L that don't divide NP, so the level times P itself. And for these unramified primes L, trace of rho sub F of Frobenius at L is nothing but A sub L, and det of rho sub F of Frobenius at L is epsilon of L times L. Now, I will say there's not really just one of these. You actually can construct one of these per prime ideal lambda and K of F lying above P. But once you've chosen such a prime ideal, there's a unique, what I mean is unique up to choice of prime ideal lambda. Okay, so look, remember, when I have an unramified prime, the Galois representation that I have restricted to the decomposition group at that prime is completely determined by the image of Frobenius. And if I have trace and determinant of image of Frobenius, then I have the characteristic equation and I understand the representation completely at that prime. So this is a very powerful condition here that says, I know exactly what the representation looks like at unramified primes. Okay, what does it look like? The trace is basically the T-elf Hekka eigenvalue, A sub L, and the determinant is basically what turns out to be the diamond elf eigenvalue, which turns out to be epsilon of L times the prime L itself. So basically, trace and determinant are like spitting out eigenvalues for the Hekka and diamond operators. That's really cool. Okay, so this really is attached to F in a very strong way, this representation. Okay, so proof for the construction of row F, you can see I would start with Diamond and Sherman chapter 9. You can also consult the Diamond-Darman-Taylor notes, page 86. Now, DS does not tackle a lot of the, it really just gives you the construction. It doesn't show a lot of the hard properties. It doesn't show absolute irreducibility, uniqueness, oddness, nor the trace and determinant properties. Now, it turns out though, DS does show that row F of Frob et al. Does satisfy the equation x squared minus ALX plus epsilon L times L equals 0 for L not dividing NP, but it doesn't show that this is actually the characteristic equation. So if you want to show the trace and determinant properties above, it suffices to compute the trace of the representation. Okay, but an even more general result than that on the Tate module, the Jacobian is actually very easily proven in theorem 1.141 in the DDT notes. If you want the result that I gave here, from that result, just base change the argument given there to KF. Okay, so that's an argument due to Brian Conrad, I think. So, okay, so that takes care of the trace and determinant properties. Absolute irreducibility and uniqueness is dealt with in Ribet's The Galois representations attached to an eigenform with Nabentypus, pages 29 to 31. I believe that uses the main theorems of class field theory and the rank and Selberg estimates. Okay, so what are we missing? We're missing oddness, right? I will prove that here because I couldn't find it proven anywhere. So for oddness, first you use Chebytarev's density theorem to see that the determinant of rho sub F is just epsilon times chi sub P, where chi sub P is the p-adic cyclotomic character. The reason for that is they agree on Frobenius's of unramified primes. You can, to see that that is true, you can just look at the characteristic polynomial and recall from an earlier video that chi sub P of Frobenius at L is L if L isn't P. Okay. So these agree everywhere because they agree on unramified primes by CDT, Chebytarev density. Okay, but then, okay, look, you can identify the Galois group of x to the n minus 1 with z mod n z cross, of course, right? So what is complex conjugation C when you make that identification? It's just -1, right? Okay, well then what is det of rho F of C? It's epsilon of -1 times chi P of C, excuse me. But epsilon of -1 is 1 for reasons I'll get to in just a second. And then I already know chi P of C is -1 because I already know that chi P is an odd Galois representation, right? So it suffices for me to explain to you why epsilon of -1 is 1 in this case. The Nabentypus epsilon always satisfies epsilon of -1 is -1 to the k for a weight k modular form. This is proven in Diamond and Sherman chapter 4. Okay. And the point is I have a weight 2. I'm dealing with weight 2 cusp forms here, right? So k is 2. So I'll have epsilon of -1 is 1. Okay, so det of rho F of complex conjugation is -1. That exactly means that rho F is an odd representation. Okay, let's end the video by talking about the residual representation. We have a Galois representation, so we should have a residual representation, right? The residual representation rho bar F from GQ to GL2 of K sub F, where K sub F is the residue field of O sub F, which is the ring of integers of K sub F, is just it's not actually just the reduction of rho sub F, because that need not be semi-simple actually in this case, but you just semi-simplify it. You take the semi-simplification of the reduction of rho F, mod K sub F, and you get rho bar sub F. What is the semi-simplification? It's the direct sum of the Jordan-Holder constituents of the reduction of rho sub F. You can see Sayre's green book on abelian analytic representations and elliptic curves. He gives a great little exposition on semi-simplifications. I just think of it is the semi-simple, the reduction itself, but like a semi-simple version of it. Okay. Assertions like the ones made above for rho sub f also hold for rho bar sub f, except for that rho bar sub f actually doesn't need to be absolutely irreducible. But if P is an odd prime, you can use the oddness of rho bar of f to check that rho bar f is irreducible if and only if it's absolutely irreducible. Almost in the same way we did something similar to that in Theorem 2, last video. Okay, so next video, I'll give a little more setup, and then we will start talking about Ribot's theorem. So I'll see you then, and thanks for watching.